Hello everyone, let us start a new topic, shear strength of unsaturated soils. So shear strength is a very important concept in soil mechanics or in geotechnical engineering because to support foundations on soils or to support any structures on the soil through foundations, the shear strength of the soil should be sufficient to withstand any loading conditions. Shear strength has interesting historical development. So let us briefly understand those historical developments and then go into shear strength of unsaturated soils. So shear strength, the concept of shear strength has been derived or brought into existence in the modern soil mechanics by Coulomb through his work inspired from Leonardo da Vinci of 16th century. So Coulomb in the 18th century has given friction laws that made the understanding of shear strength of soils. So it was Coulomb in the 18th century gave the friction laws based on that the shear strength of the soil has been derived, and he looks at soil as single phase. He does not differentiate soil and rock. So generally if you take a soil mass and the failure of the soil mass along a slip plane is observed, it could be either for rock or soils, it should act in the same manner. So a single phase system, similar to the single phase system he considers. Soil is like an entire soil is one particular continuum he has considered, just like rock mass, and he proposes the shear stress is proportional to the total stress of the soil. So based on this, the direct shear apparatus has been developed. So in the direct shear apparatus, which is very popular shear stress apparatus which we use often in soil mechanics laboratory. So in the direct shear apparatus, the soil mass is compacted, and it is like a two half system, and one half can be moved against another half. Generally the one half can be fixed. So applying the shear stress, other half can be moved relative to the other half. So a normal load of N can be applied. So divided by the cross sectional area, you should get the total stress which is acting on the soil mass. So this is a total stress that is acting on the soil mass. This is a total stress, or simply the stress which is acting on the soil mass, and a shear is applied and soil moves relative to other half, and a dial gauge can be loaded and which can be connected again to a fixed system, so that this dial gauge can record what is the amount of strain that is taking place. Similarly, one more dial gauge can be loaded, kept on the system, kept on the top of the surface. So therefore a vertical movement during the shearing operation and horizontal movement or the shear strain can be recorded at any given instance. So this led to shear stress versus shear strain diagram for different soils. For OC soils, for normally consolidated soils, they exhibit this kind of a behavior. The normally consolidated clays are loosely compacted soils. Soils are sands. They exhibit this kind of a behavior, and over consolidated clays are densely compacted. Sands exhibit this kind of a behavior, and they reach critical state at one particular strain. So, this is tau critical and this is tau peak. This is tau peak. So, this is exhibited in the system, but initially the direct shear apparatus is meant for only dry sands. This is actually meant for dry sands, and however, we have been using this for measuring the shear strength of different soils like clay soils and all fine grained soils, and also including some moisture. So, generally this is not meant for moist soils. The dry soil, dry sand soils are generally used in this particular apparatus. So, this lead to shear stress versus shear strain, and this is under one particular normal stress applied. So, similarly the tests can be repeated with different normal stresses. Therefore, one can obtain the relationship between normal stress and shear. So, you get as the normal stress increases, the shear stress, peak shear stress increases. So, based on that, either you get this kind of a linear relationship between tau and sigma. However, there is a lot of debate why this does not follow through origin, and there are some schools of thought that believe that it should be a nonlinear behavior, something like this, and it should not be linear, but let us assume that it has a cohesion and an angle of internal friction phi. But generally for sands, the line passes through origin. In case of clays, you have a cohesion term that is coming into picture, and in unsaturated shear tests also you get cohesion term, and we will discuss about that little later. So, generally this C cohesion term is absent in case of sands. So, essentially this lead to tau is equals to sigma tan phi. This is the relationship you obtain, which is attributed to Coulomb's friction loss. This is on the failure plane. So, this phi is a material constant, angle of internal friction, and sigma is normal stress or total stress, which is a stress state or state variable, and tau is a shear stress and this is also state variable. So, here one can add cohesion to make it more generalized. Some schools of thought, they do not mind adding cohesion term along with this. So, this is essentially to attribute whatever the non-linearity or to attribute the intercept which is coming into picture while plotting tau versus sigma data. So, this is what we get. So, however, Carl Terzaghi 1920, he realizes that the total stress concept should be revised, because he looks at the soil as two-phase system. Soil solids and water. When you have such a system, the strength of the soil which is exhibited during the application of the loading can differ depending on the boundary conditions. So, for example, if I have a soil system or solids plus water system, in our consolidation test also we have seen that when you apply a load, so initially there is no settlement, that is because the hydraulic conductivity of the soil is very less, that water does not come out. So, depending on the drainage condition, soil exhibits different strengths. That is because when you apply a normal load, the pore water pressure can be built up to the same value as you applied to the applied normal stress, and soil does not fail, and soil behaves in a different manner altogether. And if the water is allowed to come out through the boundaries, then it exhibits different strength. So then shear strain effects started coming into picture, and so two-phase system. So then the modification to the total stress concept has come into picture. The applied normal stress is taken up by the soil solids, that is a sigma dash effective stress plus pore water pressure. So when the drainage is absent, there is no drainage, then what is the loading condition that is applied? That is normal stress, which should be equal to the U, and sigma dash is absent. So in triaxial test, so the concept of triaxial stress has come up, where we can control the drainage very well. In the direct shear operators, we cannot control the drainage. So therefore, generally we do not use soils with certain good amount of moisture in it for shear strength testing. So we take soils in triaxial test operators, and here the triaxial test operators is designed for testing soils considering drainage conditions. So essentially the soil is seen as a two-phase system, so fully saturated conditions. So soil sample is prepared, standard sample 38 mm by 76 mm length, 38 mm diameter and 76 mm length, and the samples are fully saturated through the back pressure valve. Okay. So the sample is placed on a porous disc, and the sample is surrounded by a flexible membrane, so that it does not directly interact with the water which is available all around. So here the water is allowed around the sample, and now by applying pressure in this water, we can maintain all round pressure. So sigma 3 all round pressure can be maintained around the soil sample, and a back pressure valve is connected, and through which we can saturate the soil sample. So here once the soil is completely saturated, so whatever the amount of sigma 3 you apply, here the pore water pressure within the soil sample would be same. So whatever the sigma 3 you apply, delta sigma 3, whatever the change you make all around the sample, that will be equal to delta U in the beginning in the test. And to apply the shear stresses on the soil, a loading ram is placed and the load is applied vertically. So this deviates the stress from the all round pressure or consolidation pressure, and which shears the soil sample. So as you can control the drainage valve, so this is the back pressure valve, it is the same. So in this particular case, as you can control the drainage, and we can conduct different tests altogether. So here, as the sigma dash, the effective stress concept has been brought in by Terzaghi, which is sigma dash equal to sigma minus U. Sigma dash effective stress is the one which controls the shear of the soil. So therefore the Coulomb's equation is modified to be tau equals to sigma dash tan phi dash plus C dash. So this is effective stress, and this phi dash and C dash are the effective metal constants, or phi dash is effective angle of internal friction and effective cohesion. So tau, we do not use tau dash because water does not contribute to shear. So this is tau dash is equals to tau only. So this is the equation that is modified based on Terzaghi's inputs, and therefore now depending on the drainage conditions, the soil exhibits different strengths, and the consolidated, generally different tests can be conducted in this particular setup. So you can apply all round pressure sigma 3, and you can consolidate the soil to whatever the extent possible, or whatever the extent you want to consolidate, and after that the shearing is started, so that the shear stress are applied on the soil, and so on the soil sample you can apply sigma 1 on one direction and sigma 3 on the other direction. This is in radial direction. So, if the soil sample is shown like this, so this is in radial direction which is acting. So, this is sigma 1, this is sigma 3. So, this sigma 1 is nothing but sigma 3 plus delta sigma. So, this is a deviated stress. So, soil fails under this combination of sigma 1 and sigma 3. So, essentially you get with deviatic stress the actual strain can be measured. So, here also you can obtain for OC soil and NC soil are loosely compacted and densely compacted sands are coarse grained soils, loosely compacted sands, this is the behavior that is exhibited. So, you have delta sigma at peak, but we consider generally the critical states, critical values. So, this is delta sigma at failure, if you consider this as a delta sigma at failure under certain strain values. Then here, as the failure plane direction is not known, so we cannot directly use the Coulomb's principle, we have to utilize Moore theory as well. So, this is a Moore Coulomb concept. So, in the Moore Coulomb concept you have tau on the y axis and sigma or sigma dash on the x axis. So, then one test with sigma 3 as initially the soil state is this, initially soil is consolidated to say sigma 3. Now, keeping the sigma 3 constant, delta sigma is increased, that means this is sigma 1 and which is continuously increased and increased to one particular value where it fails. So, finally, this is the value at failure. So, we can conduct many more tests so that we can obtain the failure plane. This could be somewhat like this. So, here this is angle of internal friction phi dash, on this axis this is cut at say one particular point here and this is C dash, and if you join the center here and pole for planes is this, because on the soil sample sigma 1 is acting on horizontal plane and sigma 3 is acting on vertical plane. So, sigma 1 is acting on horizontal and sigma 3 is acting on vertical plane, this is pole for planes. So, point P. So, from pole for planes if you draw a line joining the tangent, so this is the failure plane, we can call theta. So, this is a point at which this is the failure plane direction. So, this is the failure plane direction, it should be same as theta. So, now as this side is same as this side, this is the radius of the Moore circle and this side opposite angle is theta. So, this therefore, it should be theta 2 and this should be 180 minus 2 theta and this is 2 theta and this is C dash cot phi, this fellow, so this value is C dash cot phi, and if you take sin phi dash, and this is sigma 1 minus sigma 3 dash by 2 divided by, so this is again C dash cot phi plus this is sigma 3f, these are all f's at failure, sigma 3 dash, this is effective stress we are plotting. So, sigma 3 dash plus sigma 1 dash sigma 1 minus sigma 3 by 2. So, therefore, it is sigma 1 plus sigma 3 by 2. So, if you simplify this, this comes out to be 2 c dash cos phi dash plus sigma 3 dash plus sigma 1 dash equal to sigma 1 dash minus sigma 3 dash. If we simplify this, this is sin phi, sigma 3 dash plus sigma 1 dash times sin phi dash equal to sigma 1 dash minus sigma 3 dash. If we simplify this, we get sigma 1 dash is equals to sigma 3 dash times 1 plus sin phi by 1 minus sin phi dash plus 2 c dash cos phi dash divided by 1 minus sin phi dash. So, this is sigma 1 dash into sigma 3 dash tan square 45 plus phi dash by 2 plus 2 c dash tan 45 plus phi dash by 2. So, essentially if we have two sets of sigma 1 and sigma 3 at failure, so this is from one test. If we have two sets of the data, we can determine C and phi. If we do not have C cohesion, it is for only pure sands, then if you have one set of data, you can determine what is the angle of internal friction. This is using formula, or graphically you can plot and then you can determine C dash and phi dash. These are the effective stress parameters. Similarly, here these effective stress parameters you can obtain when the drainage is allowed. So, when the drainage is open, so then pore water pressure dissipates at any given instance, then you will get C dash and phi dash. So, if the drainage valve is closed during the shearing operation, so then the shear strength that is exhibited is different, and it exhibits SU, undrained shear strength data, undrained shear strength values. So, either you get total stress parameters or effective stress parameters based on your analysis. You get either undrained shear strength or effective stress parameters like this in a given test. You can get both total stress parameters and effective stress parameters if you conduct consolidated undrained tests, but measuring the pore water pressure during the shearing, then you get both combination of effective stress parameters and total stress parameters that will be useful for the analysis for long term analysis and short term analysis. The effective stress parameters are used for the long term analysis, and undrained parameters are used in the short term analysis in case of clays. So, the Terzaghis concept of two phase system, that is introduction of effective stress concept, helped in understanding the soil behavior during shearing and the influence of drainage conditions very well. In 1959, Bishop, a British gentleman called Bishop, came up with, now it comes to unsaturated soils, how the soil behavior can be very well predicted or can be understood very well using the concept of negative pore water pressure. So, if we draw a profile, if we have a soil mass, this is the ground surface and this is the groundwater table. So far we have assumed that groundwater table is either at the ground surface or there is no groundwater table exists. So, essentially we consider only two phase system which consists of either soil solids and pore air or soil solids and pore water. So, but then in real situation we see that the soil consists of three phases. In that scenario, let us assume that the pore water, this is the groundwater table and this is ground surface, and how the in our earlier assumption where we consider that if the water table is up to the, okay, in the earlier assumption what we did is we we consider total stress distribution. So, even in the soils it may vary differently. So, this is what we considered, and effective stress, the pore water pressure does not exist. So, therefore, this is sigma or sigma dash profile. But however, if you correctly analyze the pore water pressure varies in this particular manner. Positive in the downward and negative in the upward at the hydrostatic condition. This is what we have seen when you have a capillary inserted in water table, in a beaker of water, a small capillary is inserted in a beaker of water. So, then there is a raise in water table. The pore water pressure distribution, if you plot, this is 0 here, and this is how it goes, and this is positive and this is negative. This downward positive because the water level is here, and this is positive and this is negative. Similarly, at the hydrostatic condition, this should be negative. This is the negative pore water pressure, and this is positive pore water pressure. So, above this is the condition, and if you see your total stress variation, this is how the total stress varies. So, this is sigma plot. And this is negative in this direction. So, according to the effective stress principle, the variation should be the effective stress principle sigma dash is equals to sigma minus u, u means pore water pressure. So, as we so far dealt with the two phase system in basic soil mechanics, we generally use u to indicate pore water pressure. So, here we have two pore pressures, one is water pressure and air pressure. To distinguish that, we use a suffix w here, this is water pressure. So, if sigma dash equal to sigma minus uw, then sigma minus here uw is negative. So, then this should be sigma plus uw. So, that means effective stress should be somewhat like this, and it should be plotted from here onwards. So, here whatever the uw you have, that will be here. So, this is this value uw, because sigma is 0 there, you have uw, and this is how it should vary, sigma dash. But often we have seen that generally if you take dry clays or dry soils, the magnitude of uw is very high. So, the negative pore water pressure or suction of the clays, theoretically it can go to 10 power 6 kilopascals, nearly dry state or residual state. If this goes that much, then the effective stress should be nearly infinity, and soil should never fail, but then we see failures very often. So, therefore, the contribution of uw, the contribution of negative pore water pressure to the total stress for effective stress calculations is not 100%. So, then what is the question is, how much percentage of negative pore water pressure contributes for your effective stress calculation is the question. So, there are several proposals, and there are several theories put forward, and finally it is agreed that there is certain percentage which is less than 100% will contribute to the effective stress. So, this is less than 100%. So, now the Bishop in 1959 has come up with two stress variables, two independent stress variables, but in a lumped manner. He has proposed effective stress equation, which is sigma dash is equals to sigma minus ua plus xi ua minus uw. So, here sigma minus ua is normal stress, net normal stress, and this is matrix suction. And this xi parameter is the effective stress parameter. Which varies between 0 and 1. If xi becomes 0, the equation becomes sigma dash equal to sigma. So, this indicates the soil is completely dry. So, if UA is used as gauge pressure, then this is sigma equal to sigma dash equal to sigma. So, if xi is equals to 1, then this equation becomes sigma dash is equals to sigma minus UW, which indicates completely saturated soil. This is completely dry. So, xi equal to 0 indicates completely dry soil and xi equal to 1 indicates fully saturated soil. So, generally for unsaturated soils, this xi parameter varies between 0 and 1. And this led to controlling matrix suctions in the shearing tests. So, net normal stress is applied on the soil, and how to control the matrix suction is another question. That is how the research began during that time. So, then modified shear box tests have been developed. So, here in the modified shear box tests, so the important inclusion is that the HAE disc, higher entry disc, is added. So, this is a shear box, and you have two halves here, and soil is specimen is here, and here one coarse porous stone is placed, and here HAE disc is placed, higher entry disc is placed, and this whole setup is confined in a one closed volume, airtight volume, and which is connected to one air pressure valve, and air pressure can be controlled in this particular manner. So, here the air pressure can be controlled in the system, and the air can go through this coarse porous stone, but then this higher entry disc, which is saturated with the water chamber here, and air cannot enter into it. This is closed, and this is completely closed, air cannot enter into it. So, the soil specimen, you can take initially saturated soil which is in direct contact with HAE disc, and should have a hydraulic equilibrium at the beginning. Then, so through the coarse porous stone, the air can enter, but then the air exerts some pressure on the air can enter into it, and then it can desaturate the soil sample, and air cannot enter into the HAE disc until the air pressure minus water pressure UA minus UW is equal to the air entry of the HAE disc. So, this is exactly similar to what we use in axis translation technique. So, in axis translation technique, you have a HAE disc, higher entry disc, and you have a water chamber, you can control the water pressure. So, generally we keep it is we keep this value close to the atmospheric pressure, and this is connected to the air pressure valve, and the UA is applied here. So, here the UA minus UW is applied on the soil system here. If you place a soil here, this porous disc is completely saturated, and this is the soil mass or specimen is placed here. So, initially if you keep a saturated soil specimen here, so under the application of UA minus UW, there is a load or suction load which is applied, then soil starts bleeding and water comes out, and so by measuring what is the amount of water that has come out from the soil mass, we can determine the water content, and here anyways you are controlling the suction. So, that is how we established soil water characteristic curve. So, in this particular case, in direct shear apparatus, the same technique is applied. Here the higher entry disc is placed, above this the soil sample is placed. So then you have a water chamber. Now here coarse porous disk is placed so that air can enter, and so by controlling UA minus UW, you can maintain one particular matrix suction within the soil sample. So by maintaining one particular matrix suction, under this controlled matrix suction, you are controlling UA minus UW. Similarly, the sigma minus UA is also controlled. So under particular net vertical stress sigma minus UA, you can apply on the soil system, and under this particular controlling two stress variables UA minus sigma minus UA and UA minus UW, you can conduct the shearing tests, right. So this is how the shear test, direct shear test is modified by incorporating the suction control technique, that is axis translation technique, into this one, and the shear stress at a different controlled net normal stress and matrix suction values can be obtained. We will discuss the results little later. We will only discuss now we will discuss how the triaxial test is modified. So this particular setup is also modified for exerting different stress. This is one particular way of doing it. This is by controlling using the axis translation technique, or this also can be done by osmotically controlling the matrix suction within the soil mass. So earlier I have discussed this particular system, this particular methodology. Generally, if you look at the principle, if you have a U-shaped tube, you have water levels same on both sides initially, and if you keep one semi permeable membrane, which is like a filter which you keep, and then add some salts, and the salt molecule size is such that it cannot pass through the semi permeable membrane. Semi permeable membrane is placed here, then salt is added on this side. So then if this semi permeable membrane is not present, the salt must have diffused the salt solution here, high concentration C equal to C naught, and here concentration is 0. Had it been that the semi permeable membrane is not present, the salt must have diffused from left hand side to right hand side. Salt concentration should have become same, but however, as the semi permeable membrane separates these two chambers and the salt cannot migrate through this semi permeable membrane, so water has to move from right side to left hand side and dilute this solution. So therefore, at equilibrium, if you see, so at equilibrium earlier level was somewhere here, and now the level is here, and the level on the right hand side decreases. So this is the condition. There is a osmotic head of H naught will be available here. So that means to make these two levels same, you need to apply a head, osmotic head of H naught, to bring it to this particular level. So this concept is utilized in modifying the direct shear test to conduct unsaturated shear strength tests. So essentially, you will have a soil mass, and initially it may be saturated, and then now this is connected to a porous stone, and then which is connected to a reservoir of PEG solution, polyethylene glycol. The molecular size of this polyethylene glycol, PEG, is much larger than the semi permeable membrane. A semi permeable membrane will be placed somewhere here. Then this is loaded in the same manner as it was earlier, So, this is the load that is applied, R sigma, sigma minus UA. So, here the PEG solution is placed in contact with the soil. So, as the molecules of the PEG cannot enter through this semi permeable membrane, the water will be drawn out from the soil mass and it moves down, and then essentially the PEG solution gets diluted. So, the PEG concentration gets changed and the water content in the soil system decreases, which causes a particular matrix suction maintained within the soil mass. So, this can be obtained because knowing the PEG concentration and what is the size of these molecules and what is the semi-permeable membrane size, etc., this can be obtained, and using the standard techniques this can be obtained, and the matrix suction within the soil sample can be maintained. After that, this is sheared in the same manner. So, either using axis translation technique or osmotic technique, osmotically controlled direct shear tests. So, osmotically controlled tests also can be conducted. Either way, the matrix suction and normal stress are to independently maintained, and the strength of this shear test can be conducted. Similarly, the triaxial test is also conducted in the same manner, where you have triaxial test is also conducted in the same manner, where we control the matrix suction within the soil sample by applying air pressure, and we place a higher entry disc here. So, this is the soil sample and this is a higher entry disc, and coarse porous disc is placed here, and you have a air pressure control, and so this is the air pressure line. So, through which air pressure is controlled within the soil mass, and air cannot enter into the higher entry disc until the UA minus UW is equal to the air entry of the higher entry disc. So, this is how the soil actually starts bleeding, and it attains particular it decreases the water content of the soil sample decreases when the air pressure is increased, and at equilibrium it attains one particular suction value, that is UA minus UW, and net normal stress anyways can be applied. By applying the deviatic stress, the shear stress can be by applying one you can anyways control the sigma 3 all round pressure of within the soil sample, sigma 3, and by controlling these two we can shear the soil sample by applying deviatic stress on the soil sample. So, this is similar to direct shear apparatus, and whatever the test setup, essentially the axis translation or osmotic concepts are brought into the triaxial and direct shear apparatus for modification or for controlling the matrix suction within the soil sample. So, under this controlled matrix suction environment, UA minus UW and sigma minus UA so the effective stress can be obtained. So, under this controlled environment, so the tau now becomes the equation. So, essentially the Bishop's effective stress is sigma dash equal to sigma minus UA plus xi into UA minus UW. So, if you write in terms of tau, this is sigma minus UA plus xi into UA minus UW into tan phi dash plus C dash. So, here you have another effective stress parameter to estimate, and C dash and phi dash also you have. So, these are material constants. So, xi is actually function of now moisture content, theta or matrix suction. So, these two stress variables are controlled independently in all these tests, and the shear strength of the soil sample or the shear strength of the soil sample can be determined by understanding the by estimating the material constant like C dash, phi dash and xi variation with theta. Then you can estimate how the shear strength varies with moisture content. Thank you for this lecture, and we will continue for discussing how the saturated soils can be obtained from modified direct shear operators and modified triaxial stress operators using Bishop's concept of effective stress. Thank you.